that we're doing today are a lot like the first type that we did yesterday. If you remember, there were the two that we did yesterday. We did absolute value equations with like a linear. Like if this said the absolute value of 2x plus 3 equals x plus 5, that's one of the kinds we did yesterday. You also might think of them as equal to a constant. They're very similar, right? You break it up into two cases. The only difference comes at the end. Our interpretation of the solution is very different from what we've done so far. So the first part is going to look almost exactly the same. There's a couple of little things to watch out for. But the last part of interpreting our solution is what I would imagine you would be focusing on today. Okay, and we're going to do about, I think, 5 examples, and they're all slightly different. There's all different kinds of outcomes you could get, as you might imagine, from what we've done so far. And so then when you go and practice, that's the part that you really need to focus on and make sure you understand. Some of it will be clear because we'll be talking about it together, but then I'm sure many of you have noticed you go and try to do it yourself, and you're like, wait, what? And so then you got to work through it and get through the thinking and make the connections on your own. All right, I think we can get started. I thought I was going to say something else, but now I don't remember, so let's just do it. So we are going to break this up into 2 cases. And the nice thing about this is on day 3 of this stuff, because this is day 3 of working with absolute values, some people are still kind of asking questions about why we do what we do, and there'll be an opportunity to think and talk about that a little bit more today as well. So that will come up later. This one's pretty straightforward. I look at the part that is the absolute value, and I break that up into the cases of when that is less than 0 and when that is greater than 0. Those are my 2 cases, because I'll remind you, when you're doing absolute value, if the argument of the absolute value is less than 0, what do we have to do? Multiply it by -1. But if the argument is already positive, we leave it alone. So this is me outlining my 2 cases. But I also need to know when each of those cases is actually occurring. And the important part of that is for when we interpret our solution. So I have to solve these little things. Case 1, the argument is less than 0, occurs when x is less than or equal to -3/2. Case 2, when the argument is greater than 0, occurs when x is greater than or equal to -3/2. Yes?
Are we supposed to flip the sign when we divide?
Only when it's by a negative.
Oh.
Yeah. And I could show you a quick demonstration of why. What sign would I write between those 2 numbers?
Like less than.
Thank you. Less than. And if I multiply by a negative, what sign would I write between those 2 numbers?
Oh. Okay.
All right. So the case number 1 on the left is a condition that I made up, or you made up, where the argument is less than 0. That's the one where we need to multiply by a negative to turn it back to a positive. And somebody in here said, on the first day that we were doing this, said, but wait a minute, I can put in values of x that make this positive. What if I put a 2 in for x? 2 times 2 is 4. 4 plus 3 is 7. If I put 7 in here, if x is 2 and I put 7 in here, I get -7. That's not right. Absolute value should always make things positive. But if I put 2 in for x, I've done it wrong. Where's my thinking going wrong here?
It's because it's not less than -3/2.
I would have never put 2 in here because of that restriction. X equals 2 would be in the other case. And in the other case, I'm not multiplying by a negative. So we're fine, right? We're fine. And here's one of the things that people do confuse themselves with. So take a look. This sign matches this. It doesn't have anything to do with that. Sometimes they might be the same, but that's a fluke. This sign is the same as that. Then we just solve these. Whoops, why did I do that? Greater than negative 8 over 3. Okay, very good. Move the x over, I get x. Move the 3 over, I get 2. Everybody okay with this so far? When you get that copy down, put your pencil down. And tell me this. What number is negative 8.3? Use a calculator if you want. Like as a decimal, I mean. You're like, what are you talking about? It's 8 over 3. So negative 2.67 approximately rounded, or negative 2.7. Good. What number is negative 3 over 2? Our values that are greater than negative 8 over 3, which is 2.67, are they less than negative 1.5? Which ones?
All of them until you get to negative 1.
Good answer. So in other words, some of them, but not all?
Yeah.
Are you saying every number that's greater than negative 8 over 3 is not also less than negative 3 over 2? Not all of them, right? Some of them, though. Up to that point. Because this is the answer under that condition only. And some of these numbers meet that condition. Okay? What about numbers that are less than 2? Are any of them also greater than negative 1.5? Yeah? Which ones? Some of them? Not all of them? But some of them? Do you agree? Do you see how the interpretation of this works? But that's not a very good... What am I supposed to write, Mr. Blair? Some of the numbers as my answer to this? Obviously not. But you can see that our solution is a little bit complicated. Our solution to case number 1 was when x is greater than negative 8 over 3, which is true for some values up to the point where we're no longer in that case. And there's all different kinds of solutions that you can get here. So the very best way of formalizing a solution and thinking about it that way, and based on what Lucas said, I would wonder if he's on to the right track of how you might put your solution together. But the easiest way is we're going to draw a number line. And we're going to shade in the number line and read our solution from that. Okay, so here's my number line. And it was negative 8 over 3. And negative 3 over 2. And then positive 2. So my solution says x is greater than negative 8 over 3 up until I'm less than or equal to negative 3 over 2. So how do I shade that in? That's that little part is part of my solution. This actually says all values. But I have to stop here because of that. I'll say that again. This is saying all values of x that are bigger than negative 8 over 3. So I would go on forever. But this is only under this case, so that's why I stopped there. The next one, when x is less than 2. So again, when x is less than 2, goes on forever. But I'm supposed to stop here because of that. Because case number 2 is only for values of x that are greater than negative 3 over 2. So I start here and I go to there. And I think I have now indicated all the parts of the solution, and now I write my answer with as few statements as I can as a single answer if I can.
Yesterday, after we did the 2 cases,
Yep.
and did x is greater than or equal
Yep.
to or whatever, the next line, didn't we put it so the equation was equal? Or did we continue with the greater than or less than?
Yes, you're right. I see what you're saying. You mean right here?
Yeah, those were equal.
That's because it was an equation with an equal sign in the middle.
Oh,
So take a look. This is what I said before. This sign always matches this. It has nothing to do with that.
okay. Okay, so it's an equal.
If it was an equal, then you'd be doing an equation, and it's a bit different, but yes.
Right.
Okay, so now my solution is negative 8 over 3 is less than, and less than, not less than or equal to. Look. X less than 2. Again, not less than or equal to because of that. But it included negative 3 over 2 because that was included. So do we do all this work, still split up our 2 cases, still solve those little inequalities, but then we draw a number line, shade it in, and read our solution from the number line. And this is all about, there's a whole bunch of different types of solutions that you might get. So we're going to do 4 more examples showing you different solutions. And I'm going to give you a little visual of why this is true. Again, this isn't going to help you to solve them, but it will help you understand the different kinds of solutions you might get.
Well, I was going to say, why do we do just one really long one if we're not technically including... Like, wait, can you scroll up a little bit?
We are including that middle value.
Even though, like, below it doesn't include negative over 3.
But that's why, yes, you're right, but that's why these do not include those
I
outsides.
just didn't know if you had to break it up into, like...
No, if we can write it as a single statement, we do, and in this case you can. But sometimes we will have to, but in this case I can write it as a single statement. Okay, let's do this. So here's the first question. It was the absolute value of 2x plus 3, so that's this green part. The green is always the left side of the equation. The blue is always the right side. Blue is x plus 5. You can see that if you just inspect it and think about lines. When is this absolute value less than the line? Well, look, there it is. It's below the line from there to there. It dips below, and then it crosses back over when it goes back up. So I can even visually see that my solution should be one whole interval because it's all together here. All right, let's try another one. Remember, the first part of this is very much similar to the other days that we were working on this. Yesterday and the previous day. By the way, before we do this one, I have a question for you. In some cases, this is yesterday's note. I got to scroll up to the top. In some cases, I only split it up into 2 cases for some questions. And for other questions, I have to split it up into 3 cases. How do you know when you do one or when you do the other? Because I see people trying to break the wrong ones up into 3, that sort of thing. The difference is this is double absolute value, so we need 3 cases. This is a single absolute value, so I only need 2. Good. Okay, back to business. The case, this is a weird one because it's, instead of 3x minus 6, it's 6 minus 3x. So things work out a little bit differently in this case. But when this is less than or equal to 0, remember I'm setting up these two cases. And I have said when the argument of the absolute value is less than 0, so this will be the one where I'll multiply by a negative. Right? Because I'm saying the argument is less than 0, I have to multiply it by a negative 1 to take into account for the absolute value. And then the other one, when it's greater than or equal to 0, is the case where I'm going to leave it alone. Hold on a second. Okay, we're going to solve these. And because it was negative 3x, I had to flip the sign. But this is what I'm saying. This has nothing to do with that and has everything to do with that. I said when this is negative, when this part is inside is negative, I multiply by a negative. When this part inside is positive, I leave it alone. And that's this line. I solve them to find out under what circumstances those occur for when I interpret my solution, but the top line is what defines this. Let me give you an example. Some of you might say that doesn't make any sense. When x is bigger, is going to make this negative. That's not how any of the other ones worked. When x gets bigger, how is that going to make that negative? Well, because I'm subtracting, right? So what's a number bigger than 2? 4. 3 times 4 is 12. 6 minus 12 is negative 6. But it's absolute value, so I got to multiply by a negative to give it a positive. So all values bigger than 2 will make this negative. You can see that when you see that 6 minus 6 is 0. And anything bigger than 2 will make this bigger than 6. And same thing here. If I put something smaller than 2, like, I don't know, negative 3. Negative 3 times negative 3 is positive 9. 6 plus 9 is 15. So it's positive, so I leave it alone. So be careful under those circumstances when you're subtracting x. It flips things around and it confuses people. Okay, let's solve these quickly. Okay, great. We did all this work. Now what the heck does any of it mean? So let me ask you this. Numbers that are greater than or equal to 5 over 2. What's 5 over 2 as a decimal? 2.5. Numbers that are greater than or equal to 2.5. Are any of them greater than 2? Numbers greater than 2.5, are they greater than 2? Which ones? All of them. So all of the answers for this, fit in that case. All of these solutions fit that. Okay, good. Of the numbers that are less than or equal to 7 over 4, what is 7 over 4? 8 over 4 is 2, so 7 over 4 is?
1.75.
Yeah, just under 2, 1.75. So numbers that are less than or equal to 1.75, are any of them less than 2? Which ones? All of them. So this situation is different from the last situation. You can think about it this way, but you still want to draw your number line. And by the way, draw it the right way. You got to draw the small numbers on the small side. Otherwise, you're going to really confuse yourself. Because this one flipped around, my case number 2 is over here. And what was it, 2? Yeah, 2. And my case number 1 is over here. Case number 1 says values of x that are greater than or equal to 5/2. Look, and they have to be greater than or equal to 2. But when I come down here and I start, they're all greater than or equal to 2. Values of x that are less than or equal to 7 over 4, 1.75, that are also less than 2. Well, when I start there, I start less than 2 and I'm going less than. So all those values. So therefore, x less than or equal to, because this question included, I thought I turned that off. It's positive 7 over 4 and x greater than or equal to 5 over 2. Any questions about that?
Are you showing the graph for that?
Yep. Because people would wonder, how in the world does that one work? Or maybe for the next one, you're going to wonder, why does that one work? Or for the next one. So question B looks like this. Remember, the left side is the green one, and the right side is the blue one. So it's the green one is above, because it says greater than or equal to. Green one's above for here and always will be because it's steeper, but then cuts below for this tiny little bit and then goes back above. All right, why don't we try another? Did I skip one somewhere? Ooh, I did. What happened here? Here we go. You try to set this one up. There's stages. You break out your cases, case 1, case 2, solve those cases, and then set up the inequalities that you're going to solve. To me, that's the setup. Then you solve the inequalities, then you interpret your answer. So there I've done my case 1, case 2. You can make sure yours is the same. When the argument of the absolute value is less than 0 and when it's greater than 0. Then I set up my inequalities, and noticing that case number 1 was where there was less than 0. So what do you have to do? Absolute value multiplied by -1. And then we just solve. I want to show you something in this second case, so just watch for a minute. I'm going to subtract x from both sides. So x minus x is 0 on both sides, gone. So I end up with negative 3 less than or equal to 5. Some people might do it like this. They might move the x's over, and you get x minus x less than or equal to 5 plus 3, and you get 0 less than or equal to 8. Both of these are fine. I'm pretty sure they both say the same thing. What is it saying?
That negative 3 is less than or equal to 5.
Do you agree that that negative 3 is less than?
No. Because it's equal to as well. No.
Oh, but it only has to satisfy one of them. That's a good point. But it doesn't have to be and equal to.
Oh.
It just means that if it were 5,
Okay.
that would also be okay. So I think negative 3 is less than or equal to 5 because it's less than 5. This is always true. When we say always true, I'm not saying negative 3 is always less than 5. I mean, it's true that negative 3 is always less than 5. But when I say always true, what do I actually mean by that? Like, what are we saying?
It's true, but it's not lesser.
That's correct as well, but that's not what I'm saying.
Doesn't really matter.
Max?
It's true for every value of x.
Thank you. It's true for all values of x. Doesn't matter what x is, this will always be true, which also means doesn't matter what x is, this is always true. Put any x you want in there. I subtract 3 and I add 5. That one's always going to be less. Think about what it's saying. X minus 3 is less than x plus 5. Yeah, that will always be true. Okay, so always true for all values of x. The other thing I want to point out before we go further is when we're solving equations, some people like to always keep their x's positive. So I could imagine at this stage, somebody doing this. You get negative x plus 3 less than or equal to x plus 5. You move the negative x to the other side and move the 5 over. So I get negative 2 less than or equal to 2x. Divide both sides by 2. So which one's correct? In fact, they're both saying the same thing. The sign's pointing the other direction, but the x is on the other side. I think this is confusing. The red one is confusing. We don't usually look at it like that. We do things by a standard for a reason. It makes it easier for us. When I say x is always greater than or equal to negative 1, that has more meaning to me at least than negative 1 is less than or equal to x. Because we're talking about x changing, not negative 1 changing. So I would rewrite this. And if I move the x to the other side, I got to flip the sign. I would rewrite it like that. But that's why I always move x to the left, even if it makes it negative. You can do it either way, but just make sure you do it correctly. Okay. So this is interesting. Values of x that are greater than or equal to negative 1. Are any of them less than 3? How many? All of them? Not all of them. 10 is greater than negative 1, but it's not less than 3. So some of the values work, some of them don't. And the other interval is just always true. What does that mean? It means this works for all values. Our solution to this one is the entire interval, the entire domain. Let's draw this out. So I've got negative 1 here, and I've got 3, and I don't have a third number. Values of x that are bigger than negative 1, but less than or equal to 3. So I'm going to start there, and I'm going to go until I stop at 3, because that's where case number 1 ends. What am I going to do for the other interval? In the other interval, it's always true. So how do I read this as my solution? Max?
X is greater than or equal to negative 1.
Very good. And why do you include the equal to? Remember, because of that. And that came from the original equation. Yes?
Wait, so sorry, since that one's always true, you just can assume that the x is greater than or equal to 3, just the whole thing is going to be true?
That's right.
Okay.
That's exactly right. See, the interpretation of these is the hard part. It's not necessarily intuitive. It's not obvious. But if you think about this, then maybe it does make sense. What's the visual for this one? So look, starting at 1, the blue line is above, or the green, you might say the green line's below, because it says when is the green below the blue. So the green is below, the blue is above. And then right here, where we change our cases, look, those lines are parallel. It's below and it's always going to be below. In the other cases, it was like slanted more, so it caught up and overtook it again. But in this case, it's always going to stay below. There's all these different cases that can arrive in these. Any questions? We're going to keep going.
For the top one, would you accept both cases? So like 0x is less than 50? Like,
Yes. Yeah. Absolutely. Yeah. Go ahead. You can get started on this one.
So if it's extraneous, you just kind of use it. So you don't use that whole case.
I've set up my cases. And I have set up my inequalities. And now we just solve. Is everybody good? So, case number 1, x is less than 1 is the solution. If any part of that solution is in the domain of case 1, then those count as answers. So are any numbers that are less than 1, are they less than or equal to 2? Which ones? All of them. So case number 1 is going to have some solutions. Case number 2, x is less than -1. Are any values of x less than -1 in that domain of x greater than or equal to 2? No. This is extraneous because it's not in the domain. So we will have no solutions there. So I've got... I don't know that you really have to include -1 on your number line. I would say you don't. I've got my 1 and my, well, I'm going to make that 2. And then I've got my 1, but my -1 would be even further down. And again, this is saying x is less than 1. That's in this domain. So that starts here and goes on forever. What does this one look like? Absolute value of x minus 2 greater than 2x minus 1. So this is why we have an extraneous, because in case number 2 is this part of the absolute value, and it only goes to 0. But if I extended it, you can see that it would be crossing, and look, it looks like it would cross at -1. And that's the extraneous solution that we get. But it's not in the domain because I'm not using that line anymore. I'm using this line. All right, one more. Before you start on this one's interesting because we just did 4 in a row and they were all, you may not have noticed, but they were all set up the same. And I apologize in advance if anybody here has already done this, although I maybe cut you off too quick and you didn't get started. But if you had already started this one, I would imagine, maybe not in this room, but over time, I've seen people do this. To split up their cases. What is the mistake that this person has made?
Has to be whatever is in absolute.
Why do you think they might have done this, though? Because all the other questions were just the left side. And some people might have missed day 1 of this stuff or just not be thinking. Again, it's so important that you understand why we're doing what we're doing. You're not just taking one of the random expressions that's in here, the first one you come across, and doing that. Right? It seems silly when you point it out, but it's amazing how our brain develops habits and notices patterns without us even realizing it, and then starts using those patterns. And you might think that would never happen to me. It does. So be careful. But this should be x plus 3 less than or equal to 0. X plus 3 greater than or equal to 0. Right? Because that's what's in the absolute value. Again, watch case number 2. I subtract x from both sides. X minus x is 0, so I get 1 less than or equal to 3 minus 2 is 1. For what values of x will this statement be true, that 1 is less than or equal to 1? Right? It's always true. 1 is always equal to 1, no matter what x value you choose. Yeah? Adam?
So, like you were saying, you can get 1 equal to 1, or you can get, like I just did where it says 0 is equal to 0.
Yeah, so that means the same thing. Or if it came up as, which it wouldn't in this case, but if it came up as 1 is less than or equal to 2, it's the same thing. Yeah. Still always true. This is interesting too. X is less than or equal to -3 is the same as that. There's sort of a graphical reason why this occurs, but it doesn't really matter to us in our interpretation, I don't think. When is x less than or equal to -3 and less than or equal to negative 3? Well, always. So these are the same, so it'll be true for x is less than or equal to negative 3. And this one's always true for x is greater than or equal to negative 3. So does anybody know what our solution to this one's going to be? Huh? X is an element of the real numbers. That's exactly right. All values of x work for this one. So if I split it up at negative 3, and for this one, it's below negative 3 when it's below negative 3, so it's all those. And this is always true when x is bigger than negative 3, so all those. So that's our solution. So the visual of this one, take a look. You could have it, I think you could imagine, such that the line actually cuts under the absolute value and it's just always below or always above. But in this case, when is x plus 1 less than, so it's less than there, and it's equal to there. So it is always less than or equal to that graph.